And 5, 4, 3, 2, 1. It is now 6:30. It's time to launch our program this evening. Before we get started with everything, I just have a few reminders. The first one is that this program is live and interactive, and we want you to ask questions as you have them. If you're watching this on a computer, you can add a question by going to the control panel and then going down to questions. If you are watching this program on a smartphone, there is a questions button that looks like a question mark that you can tap. We will be accepting your questions throughout the program, but we will be answering them at the very end in our Q&A section. Point number 2, while we are recording this program live, we will be posting it to our YouTube channel so you can watch it later. Our YouTube channel is Tampa Hills Live, and you can find a link to our YouTube channel by going to our website, hcplc.org/events, and clicking on the recorded programs button. Last point, we love getting your feedback for all of our virtual programs, and at the end of this one, you'll receive a brief survey email. We really appreciate it if you could just take a few minutes to fill it out so we can get some feedback to help us improve our programs in the future. So I will pass it off to Miss Jenny Hodges now and Natalia, and I will say farewell to you all and enjoy the program this evening.
Good evening, everyone. My name is Jenny, and I'm with the Tampa Hillsborough County Public Library. Tonight, I am joined by Natalia Guerrero, a graduate of MIT and a current PhD student researcher in the Department of Astronomy at the University of Florida. Natalia's research interests include the study of planets beyond our solar system and the story of their birth, evolution, and death. Natalia is also a test science consultant for NASA's Transiting Exoplanet Survey satellite at the MIT Cavalli Institute for Astrophysics. Welcome, Natalia.
Thank you. Wonderful to be here.
Before we get into tonight's program, we want to give a couple of book shout-outs. For our younger readers, we recommend Ada and the Galaxies, written by renowned physicist Alan Lightman and illustrated by Susanna Chapman. This book uses actual photographs taken by the Hubble telescope, and then they're layered with original watercolor illustrations, and it makes the stars truly come to life. I highly recommend this book. For our older readers, our subject matter expert recommends The End of Everything, Astrophysically Speaking, and you can find these titles at hcplc.org/books. We're also going to give a shout out to our Overdrive digital collection. Staff has curated a great list of titles to celebrate the launch of the James Webb Space Telescope. There will be a link to this book list in the chat. Now it's time to learn about astronomy and the James Webb Space Telescope with Natalia. I will be turning off my camera, but I'll be back at the end for the Q&A session. So make sure to put your questions in the chat. See you in a little bit.
Great. So I'm going to go ahead and share my screen. Let's get this set up here. All right. Let's try this again. There we go. All right. Hi, everyone. My name is Natalia Guerrero, and I am so excited to be here just over a week before the launch of the James Webb Space Telescope. First, a little bit about myself. As I was introduced, my name is Natalia Guerrero, and I study exoplanets, or planets around other stars. And in the past, I've done so using another NASA space telescope called TESS. And I've included an illustration here of TESS and how it searches almost the entire night sky, and it has found thousands of exoplanets, or planets around other stars. And we're hoping that some of these may be also observed by James Webb Space Telescope. And I'll tell you a little bit more later about why that's so exciting. So the start of the show is the James Webb Space Telescope. So it is launching December 22nd, and so that is going to be next Wednesday from French Guiana. There's a launch pad there. You can learn more about it at the website I have linked below. So breaking down a little bit of the anatomy of this spacecraft. So you see these big reflective shields that are kind of like a kite underneath the Space Telescope. These are actually to block the sun's light and to keep sunlight, which is really bright, from entering the really sensitive cameras on the telescope. So there's 5 of these heat shields, and they're each really, really thin. They're like a piece of paper or Kleenex. They're very delicate, and they will ship unfolded. They'll launch folded, and then they'll unfold into this beautiful heat shield that's about the size of a tennis court. And then there's the gold reflective honeycomb shaped mirrors. And so light will bounce off of those, off of a second mirror, which is out in front of the Space Telescope, and then into the camera, which is the telescope's eye, which is this black piece at the middle of the glass mirrors. So this is going to be James Webb's eye. And how does this eye work? It uses infrared light. And so we see light in the visible. We can see everything from really blue light all the way to really red light. And it might sound weird that I'm using, that I'm saying this sort of backwards from our normal rainbow, which is red, orange, all the way to violet. That's because astronomers use we flip the rainbow around. We think about blue light as being high energy and short wavelengths. And we think about red light as being lower energy and longer wavelengths. So we go from short wavelengths to long wavelengths. So James Webb is going to look at long wavelengths of light, redder light. And what's it going to be doing? So James Webb has this really interesting orbit where Earth goes around the sun in a circular orbit, and James Webb is going to be orbiting outside of Earth's orbit at a gravitationally stable point called L2. So this is a place where it can be without getting perturbed by any other thing in the solar system. And so it's going to go in circles around that point in its orbit, and that'll take about 2 or 3 weeks. So let's talk a little bit more about infrared light. So I keep using this word infrared, but infrared light is also heat. So if you've ever heard of a thermal camera, it can see in the infrared. So here's a picture made by an artist of a horse seen in the infrared. And you can see just under its skin and the patterns of heat that it's giving off. And so we use thermal imaging here on Earth for making art and also for industry. Thermal cameras are really useful for a number of jobs, applications, even in the military. So having a thermal camera allows us to see warm things in outer space. So I'm going to talk about what some of those warm things are. So here I have a picture of that's well known as called the Pillars of Creation. And so this is a part of the Eagle Nebula, which is in one arm of our own Milky Way galaxy, about I would say 1/10 of the way of the whole size of the Milky Way galaxy away from us. And so you can see that these big pillars of creation, they're made out of dust. And dust is a really great place for stars to be born. It has a lot of good material that stars can be made of. But the problem is that we can't see through the dust to where these baby stars are being made. And we want to see them because that's really important to understanding how stars are formed and how our own star, our sun, is formed. So how do we see through the dust? Well, it turns out that dust is cool. It doesn't emit a lot of infrared radiation. So light from the stars inside the pillars can travel through the dust if it's in the infrared. So this image was taken with the Hubble Space Telescope. And Hubble can see a little bit of the way into the infrared. So I'm going to next show you what the Hubble infrared image looked like. Wow, right? All of these stars just pop out of nowhere. And that's because the infrared allows us to see all of these stars being born and allows us to see through the dust. So this is just one really important example of how powerful it is to have a really great infrared telescope in space. So before I go any further, I wanted to give everyone a crash course on the history of everything from the beginning of the universe onwards. So first there was the Big Bang, and then shortly after the Big Bang came the first light that came out of the universe when all of the material combined and made photons. And then after photons, not a lot went on for quite a while because all of this light was traveling through the universe, but it was still too hot for any matter to be cool enough to come into contact with each other. But then, after a long time, it was cool enough that matter could start condensing. And this earliest form of matter is called dark matter because it doesn't emit light. However, it can attract dust, gas, things that do emit light. And so the dark matter formed these filaments called the cosmic web. And you can see in this animation as light and gas and dust and those things that emit light were able to come along these filaments of the cosmic web and start to form stars. And those stars grew and then exploded. And then the remnants became new stars. And these stars aggregated and became the earliest galaxies. And those galaxies merged and made new galaxies and on and on and on. And that was the beginning, really, of the history of our galaxy. And so we want to be able to see these earliest times. We're able to see the earliest light using radio telescopes, and microwave telescopes, something called the cosmic microwave background. But to see the earliest stars, we need to look far into the infrared. We can do a little bit of this with the Hubble Space Telescope, and actually this has been an incredibly powerful tool. Hubble looked into what's called the Hubble Deep Field, looking far back, both in space and time, at the darkest part of the sky it could. And what it saw there were millions of galaxies that were, the farther it looked, the further back in time it could see. So it could see the oldest galaxies and light from the oldest galaxies traveling towards us. However, it wasn't able to see the light from the earliest stars. For that, we need a more powerful telescope. We need a telescope that can see redder light. That telescope is James Webb. So that's one of the things it's going to be looking at, is the earlier stars, is these earliest stars in the universe. So another thing it's going to be looking at are the galaxies themselves. So if you've seen animations or drawings of our galaxy, you've seen that it looks like a spiral. It looks like this beautiful whirlpool, and other galaxies look like ellipses. And this animation shows two galaxies that are merging and pulling material away from each other. But if we look at the earliest galaxies, they're kind of messy. They're clumpy and lumpy. They don't look anything like this. So we need to fill in some of that story of how did these galaxies that looked so different early in the universe's age look so different now? What happened? So that's another thing that James Webb is going to look at, is the evolution of galaxies throughout cosmic time. And I'm really excited about that because I'd like to see, are these galaxies merging? What's happening? All right. So the next thing I'm going to talk about is a little bit more about how James Webb works in a different way. So we've talked about infrared light, but the other thing, so this is light coming from our target star, coming from the sky. We've talked about how it enters the telescope, but another thing that it can do is split the light up. And the way that it does this is it uses something called a grating that can split the light into its different wavelengths. So here you see the light coming in, and then you have a red arrow and a blue arrow. So the wavelengths of light are being split along this grating, which acts basically like a prism. If you've ever seen one of those create a rainbow, or a CD can create a rainbow really easily. And from that, we can get a spectrum. We can see the spectrum of the star's light. We can see all of the different colors in that light, and we can see basically the fingerprint of that light. What elements are in the star that's shining, or the galaxy, and we can better understand what it's made out of. So one of the big questions that I'm interested in my own research is, what are the ingredients for life? We know about all of the elements on our own planet. That's kind of like our pantry that we pulled from to make life. But on other planets around other stars, we don't know if those ingredients are the same or if they'd be different. And if you put different ingredients in combination, will that also create life? So we can use the light coming from the star to understand what elements, what molecules a planet has available. So the way that I have worked on detecting planets around other stars is not by directly taking pictures of those planets. They're too far away and too faint. We can barely even see, we can see the stars with our eyes, but we need telescopes to really take a good look at them. So what we do is, as the planet crosses in front of its host star from our point of view, a tiny dip of light is blocked out, and that's how we detect the planet. The other thing that happens is that the planet is backlit by its star. Light from the star passes through the planet's atmosphere and gets emitted or absorbed, and eventually makes its way to a conveniently placed telescope like James Webb. So a little bit more about how this actually works. So you have the light coming from the star with a number of wavelengths, and then it encounters the planet, and the planet absorbs or emits some of that light. Whoopsie daisy, let's start that again. So we have the light coming from the star, has a bunch of different wavelengths, and then when it's absorbed by the planet's atmosphere, some wavelengths survive, some get absorbed. And based on what wavelengths survive or get absorbed, we know that certain molecules are causing that emission or absorption. And so then we can put together what this planet is actually made of and what's in its atmosphere. Does it have carbon monoxide, methane, water, sulfur, other gases, things that will tell us, is there life here? Or is this just a geological process of the planet? So this is a really interesting question that I'm very excited for James Webb to answer. Already 70 exoplanets are on the list to be observed by this telescope, and I cannot wait. So if you're interested in keeping an eye on Webb as it gets ready for launch, it's happening in 8 days. You can sign up to attend as a virtual guest. They have a launch page and all sorts of information on their website. And you can even set one of the tabs on your computer open to a countdown. I'm really excited and will definitely be blocking out my morning. It launches at a little bit after 7 a.m. on next Wednesday morning. So I think I will pause there and we can chat and take any questions. Thanks, everyone.
Great, wonderful, very interesting, thank you. We do have a couple questions. You ready for our first one?
Sure.
Okay, so we know that Webb was originally supposed to launch back in October, and that didn't end up happening. But what are some factors, like why didn't it launch? And what else can affect the launch date and the location? Like, why is it being launched down in South America instead of from somewhere in the United States like the Kennedy Space Center?
Yeah, that's a great question. So I'll first tackle the first part, which is, why did it take so long? Why did it get delayed and get delayed? And part of that is because this is going to be, I believe, one of the largest telescopes that NASA has ever launched. And so it is incredibly complex, and they need to make sure they test it and test it and test it again to make sure everything's right. And so there's a lot that goes into making sure everybody's organized and on track and has all of the deadlines planned out. So that's part of it, is making sure that everything is working, and when something doesn't go according to plan, readjusting and changing your timeline such that everything works when you actually do launch. The second part of that question was asking about, why South America? Why so far away? We're in Florida, we're spoiled. We get to watch launches from Cape Canaveral all the time. So the answer to that is actually because of the position on the Earth matters for launching something. If you're closer to the equator, you're able to get a little bit more of a gravitational kick from the Earth when you're launching something. And that's especially important when you're launching something as heavy as James Webb. It's using a really large booster, and you have to get all of this mass off the Earth. So you need all the help you can get. And so that's why they're launching from a lower latitude, closer to the equator.
Great, thank you. Okay, so we know that Hubble has been around sharing images for over 30 years now. Do you expect the life expectancy for Webb to be around that time? Or, you know, because we know when it's done, it's done. There's no going up in space to fix anything that breaks. So fingers crossed, you know, that there's no issues once it gets up there. But have they projected how long they expect to see images coming from it?
I believe the plan right now, and the plan has always been with any telescope, is we take it not one day at a time, but a few years at a time. And so Hubble has had many extended missions, but of course it was designed to last a long time. And so it is in its fourth decade of operation. And so yes, the idea is that James Webb is built such that there's very few moving parts. It has a lot of propellant. It can last out there for a long time. It has a lot of backup systems such that we hope to get decades of use out of this flagship mission.
And will Hubble continue to send images?
Yes.
Even once Webb is up? Okay.
That's the idea, is that these two are besties and they can work together.
How close or far away are they in space from each other?
So Hubble is orbiting the Earth in a very close orbit. So Hubble, I believe, goes around the Earth every 90 minutes, whereas Webb is going to be sort of trailing the Earth out at this L2 point. So it's going to be many millions of miles, or I don't believe millions of miles away, but it's going to be pretty far away. It's going to take about 2 weeks for it to get there.
Great. So as a researcher, are there any theories about what might be found in other planets' pantry for what is needed for life?
So we're hoping, so one of the targets that I'm really excited about is this TRAPPIST-1 system, which is a 7-planet system, 3 of which their planets are in, they are warm enough to have liquid water on their surface. So I'm really excited to see data back from those planets, because we'll be able to see, is there water on the surface? What else is on the surface? And even if we don't see a clear signature of something that means life, we will see so much more information about what's going on this planet. If we see methane, maybe that's related to volcanoes. If we see carbon dioxide, maybe that's related to weathering. There's all sorts of things that we can learn from atmospheric studies of exoplanets.
That's so neat. So James Webb, is the technology new for Webb, or is it something that's just come about because researchers have started to ask different questions and there's been different theories proposed? Or is it simply because, you know, 30 years ago when we did Hubble, we just didn't have the same knowledge that we do now?
Right. So Webb has been in development for about 20 years. And so not all of the technology is the most up to date, but they did have to redesign their detectors specifically for Webb, because this deep infrared, this really red thermal light, you had to design a new, very sophisticated type of camera for that. And then I talked about the sunshades. A lot of engineering thought went into creating a sunshade like that that could unfold very carefully in space. So there was a lot of innovation that went into Webb.
All right, let's see our next question. Do you expect the Webb version of the Hubble Deep Field to now reveal many early galaxies in the infrared wavelengths, revealing many more galaxies? Yeah, so I guess you're expecting Webb to reveal many more galaxies?
Yes, I'm very excited about that, because these will be the earliest galaxies in the universe, the very oldest ones.
Oh, that's really neat. So if we have anybody watching today or on our recording that wants to get involved with the James Webb Space Telescope, is there any way that they can do that?
Yes. So right now, actually, this week is the last week for the Webb Unfold the Universe art competition. So this is inviting anybody in the community to make a piece of art, a drawing, a song, anything inspired by Webb, inspired by what you think this telescope is going to discover, and submit it to the NASA website. And I believe someone is going to post a link in the chat for how to do that. It's called Unfold the Universe.
All right, we'll see if someone puts that into the chat for us. Are you submitting anything? Because I know you're an artist, or are you not allowed to do that since you're also an astronomer?
I'd love to. I hadn't thought about that yet, but maybe I'll do something this week and submit it. That's a great idea. Thank you for submitting it.
Yeah, you're welcome. All right. Yep, and someone did drop the link into the chat. So you guys can go take a look at that and see if there's anything that you'd like to put together and submit to Webb or to NASA by the end of this week. I don't see that we have any more questions. Let me take a quick peek. All right. So does the Milky Way, do we have new stars and planets forming, or have we discovered all we're going to find?
So the Milky Way forms about 1 to 10 stars per year. We're still making new stars within the Milky Way. And not all of those stars are stars that are bright enough for us to see. If you think the Milky Way is about 100,000 light years across, and our solar neighborhood is about the nearest 300 light years or so. So that's the area of space that I'm interested in for discovering exoplanets, because that's where our telescopes can see best for looking at exoplanets. But astronomers interested in galaxies, they're interested in things on the other side of the universe. They're interested in, or not on the other side of the universe, things outside of our galaxy, things that are thousands of light years away.
All right, one more check. And I think we have answered all our pressing questions. So yeah, thank you, Natalia, for joining us this evening and sharing your expertise. It was really a fascinating program. I really enjoyed it, and I'm sure I speak for everyone that watched it when I say that we're all really excited to see the images that will come from the Webb Space Telescope, and I can't wait to get my first, Webb calendar with the images, because I love seeing the Hubble, and I think Webb is just going to be amazing. And so everyone, you also want to mark your calendars for our next event with Natalia. It's called You Can Be a Citizen Scientist, and it's going to be on Monday, January the 24th at 6:30 p.m. And we're going to drop the link to register also in the chat. So great. Thank you so much for joining us today, Natalia.
Thank you.
All right. So for those of you, if you need to contact the library in any way, you can call us at 813-273-3652 or hcplc.org/contact. And we also highly recommend that you explore our upcoming events and classes at hcplc.org/events. So everybody take care, have a good night, and we'll see you on January 24th. Good night.
Bye.